We now study how to integrate in polar coordinates. So we begin by working with a shape known as the polar rectangle. This is the analog of the rectangular region we worked with 2 videos ago when we first started studying double integrals. So a polar rectangle is a shape whose sides have constant radius. See here, r equals a, r equals b, and constant theta values. So this is the ray theta equals alpha, this is the ray theta equals beta. So a polar rectangle can be described as the set of all ordered pairs are theta, such that a is less than or equal to r less than or equal to b, and alpha is less than theta less than or equal to beta. Now consider a function f of r theta over a polar rectangle R. Much like we did in Cartesian, we divide the interval into m subintervals of equal length. Delta r equals b minus a over n, or over m rather. And we divide the interval alpha beta into n subintervals of equal length. Delta theta equals beta minus alpha over n. So this interval here, that should have been the interval for r, so a to b. So this means that the circles r equals r sub I and the rays theta equals theta sub j divide the polar rectangle into smaller sub-rectangles r sub ij. Now recall that in a circle of radius r, the length s of an arc subtended by a central angle theta radians is given by s equals r times theta. Furthermore, notice that the polar rectangle r sub ij looks a lot like a trapezoid with parallel sides r sub I minus 1 delta theta and r sub I delta theta, and a width of delta r. Hence, the area of this rectangular region would be delta A 1/2 delta r times the quantity r sub I minus 1 delta theta plus r sub I delta theta. If we now let r sub ij star equal this 1/2 r sub I minus 1 plus r sub I, then we can rewrite the area as r sub ij star times delta r times delta theta. So the volume of the thin box that is above r sub ij is given by f of r sub ij star theta r sub ij theta I sub ij star times delta a. Right, and delta a is of course r sub ij star delta r delta theta. So the total volume would then be approximated by this double summation here. Using the same notation as we did with Cartesian when we first started studying double integrals, we will get the following. The double integral over the region R of f of r theta dA is this limit right here. Well, that's great if we're given a function in terms of r theta. What if we're given a rectangular function? That is, it is a function of x and y. Well, in our previous discussion, if the point we use is in the rectangular coordinates xij, yij, then we just simply use the conversions, x equals r cosine theta and y equals r sine theta that we studied way back when we were studying vectors, to rewrite f of x sub ij star, y sub ij star as f of r sub ij star times cosine of theta sub ij star, r sub ij star and sine of theta sub ij star. This then gives us the double integral of f of xy dA is equal to this limit in polar coordinates now. And so this is how we would integrate in polar, or how we would convert a rectangular integral into a polar integral. Right, so for a continuous function f on the domain that is given in in polar coordinates, theta 1 less than equal to theta less than equal to theta 2, and r sub 1 of theta less than equal to r less than equal to r2 of theta 2. This should be, that should not be a theta 2 there, that should just be a theta. Then the double integral over the domain D of f of xy dA is the integral theta 1 to theta 2 of the integral r1 theta r2 theta f of r cosine theta r sine theta times r times dr times d theta. Now, a very common mistake that is made is students will forget this extra r when they convert. Remember, this extra r must be included. So dA is r, dr, d theta. That whole thing is dA. So let's go ahead and evaluate this double integral. 1 minus x squared minus y squared, where r, the region, is the unit circle on the xy plane. Well, the unit circle, we know, can be defined as 0 less than equal to less than 2 pi, and 0 less than equal to r less than or equal to 1. So our double integral is the integral from 0 to 2 pi, integral from 0 to 1. Now we just have to convert this 1 minus x squared minus y squared into polar. Well, if we notice, we can write this piece here as negative x squared plus y squared, which is just simply r squared. So we can write this as 1 minus r squared, and then dA is r, dr, d theta. And again, the order in which you integrate dr d theta or d theta dr does not matter. The only time it would matter is if r is dependent on the angle theta. Then you'd have to do dr first and then d theta. Right, so integrate. I actually do flip the order first here, so let's go. This is the integral from 0 to 1, integral from 0 to 2 pi of r minus r cubed d theta dr. And the only reason I do this is because there is no theta. So the integral from 0 to 2 pi of just d theta is 2 pi. So we get 2 pi times the integral from 0 to 1, r minus r cubed dr. So this becomes 2 pi times the quantity r squared over 2 minus r to the 4th over 4, evaluated from r equals 0 to 1. We wind up with 1/2 minus a quarter, which is a quarter, times that by 2 pi, and you get pi over 2. So let's now evaluate this integral. So the integral of x plus y dA, where the region is the set of xy such that 1 is less than or equal to x squared plus y squared, which is less than or equal to 4, and x has to be less than or equal to 0. So let's try and sketch out this region. Right, so x squared plus y squared equals something, right, is a circle. So x squared plus y squared equals 1 is the unit circle. So that's 1, 1, 1, and 1 all the way around. Right, so this would be the circle x squared plus y squared equals 1. X squared plus y squared equals 4 would be a circle of radius 2. So something like this. Right, so what we're concerned with is this area that's between the two circles. However, we also have the stipulation that x is less than or equal to 0. So actually, the region that we're working with is just this region here. Right? Okay. So we can describe this easier in polar. So the radius is obviously going to be between 1 and 2. But what about theta? Well, if x is less than or equal to 0, the angles that correspond to that are all the angles over here, right? So it's pi over 2 to 3 pi over 2. And so this would be our rectangular region described as a polar region. So we can now go ahead and integrate. So integral over d x plus y dA would be the integral from pi over 2 to 3 pi over 2, integral from 1 to 2, now of r cosine theta plus r sine theta, r dr d theta. So we have the integral from pi over 2 to 3 pi over 2, integral from 1 to 2. We can factor out that r from cosine theta sine theta, so we're left with cosine theta plus sine theta. Of course, I multiplied by that r as well to get r squared, dr d theta. So this is the integral from pi over 2 to 3 pi over 2 of r cubed over 3 times cosine theta plus sine theta, evaluated from r equals 1 to 2, and then we still have that d theta. So we'll wind up with 8/3 minus 1/3 is 7/3. So 7/3 times the integral pi over 2 to 3 pi over 2 of cosine theta plus sine theta d theta. Right, so 7/3 times the quantity of sine theta minus cosine theta, evaluated theta equals pi over 2 to 3 pi over 2. Now cosine theta at these two angles will be 0, so we get 1 minus 1, right? Sine of 3 pi over 2 is -1. Sine of pi over 2 is +1. So this becomes -14 over 3. So let's now find the volume of the solid that lies under the paraboloid, z equals 4 minus x squared minus y squared, and above the disk, x minus 1 squared plus y squared equal to 1 on the xy plane. So to try and describe this region D, first, let's notice that the disk can be written in terms of can be expanded this way. X squared minus 2x plus 1, then plus y squared is equal to 1. So this means that x squared plus y squared is equal to 2x. And so we have r squared is equal to 2r cosine of theta. Now notice that this would mean that either r is 0 or r is 2 cosine of theta. So we have 0 less than or equal to r less than or equal to 2 cosine of theta. Now this means, right, cosine of theta has to be greater than or equal to 0. So negative pi over 2 would have to be less than or equal to theta, which is less than or equal to pi over 2. So our region can be described as the set of all ordered pairs r theta such that negative pi over 2 is less than or equal to theta, which is less than or equal to pi over 2, and 0 is less than or equal to r, which is less than or equal to 2 cosine of theta. So our double integral, or our volume rather, is the double integral over the domain D of x plus y, of 4 minus x squared minus y squared dA. So this equals the integral, I'm going to move it down a little bit, integral from minus pi over 2 to pi over 2 times the integral from 0 to 2 cosine of theta of 4 minus r squared r dr d theta. So we get the integral from minus pi over 2 to pi over 2 of 4r minus r cubed dr d theta, integral from 0 to 2 cosine of theta. Now of the 4r minus r cubed dr d theta. So this will give us the integral from minus pi over 2 to pi over 2 of 2 squared minus r to the 4th over 4 evaluated from r equals 0 to 2 cosine of theta d theta. So this is the integral from minus pi over 2 to pi over 2 of 8 cosine cubed theta minus 4 cosine to the 4th theta, and then d theta. Now if we plug this in, we're going to find that this will give us 5 pi over 2. This would be a long integral to do by hand, but since this is calculus 3, we can just use technology. So we want to evaluate the area bounded by the curve r equals 4 cosine of theta. Now this is what this curve looks like. So if you notice, we have 8 petals, right? 1, 2, 3, 4, 5, 6, 7, 8. The area in each of these petals is going to be identical. So what we can do is just take one of these petals, calculate the area in it, and then multiply by 8. So let's go ahead and define this one petal to be our region of integration. So cosine of 4 theta will have to equal 0, which means that 4 theta is equal to plus or minus pi over 2, and so theta would be plus or minus pi over 8. So our region, this D, is the set of all ordered pairs r theta such that negative pi over 8 is less than or equal to theta is less than or equal to pi over 8, and 0 is less than or equal to r, which is less than or equal to cosine of 4 theta. So remember area is the double integral over the domain of dA. So that's the area of one of these petals, right? So total area would be 8 times this double integral. So if we set it up, we're going to have 8 times the integral from minus pi over 8 to pi over 8, integral from 0 to 4 cosine of theta, r dr d theta. So this will give us 8 times the integral, negative pi over 8 to pi over 8, r squared over 2 from 0 to 4 cosine of theta d theta. So we'll have 8 times the integral from minus pi over 8 to pi over 8 of 8 cosine squared theta d theta. Right, so this will equal I am terribly sorry. I need to start this all over because it was supposed to be cosine of 4 theta, not 4 cosine of theta. So this is going to be incorrect. This needs to be cosine of 4 theta. This needs to be cosine of 4 theta. So this will become cosine squared of 4 theta over 2d theta. And if you go and plug this in, and I'm actually going to do this one out by hand because this is not too long. So we'll get 4 times the integral from minus pi over 8 to pi over 8 of 1/2 plus a half cosine of 8 theta d theta. Right? That's using one of the trig identities. So integrating this, we'll get 2 theta from minus pi over 8 to pi over 8 plus 1 over 16 times sine of 8 theta from negative pi over 8 to pi over 8. So we'll get pi over 4 plus pi over 4. This entire piece here will just go to 0. And so this leaves us with pi over 2 as our volume. Okay. So that is going to be it for polar integration. In the next video, we begin with triple integration.